In the last session, we looked into the uh, derivation for the energy associated with flowing fluid, and we came to a conclusion that if there is a fluid flowing, it would have essentially an energy equivalent to PV, which is necessary to continue the motion or to continue against the resistance caused by the fluid itself, and that is the energy associated with flowing fluid. Now, we'll start with the total energy associated with the flowing fluid. What is the total energy that a fluid is carrying as it enters into the control volume or it leaves the control volume? So it is the energy which is associated with the mass, the amount of material which is entering into control volume. Basically, if we look, if the fluid is non-flowing, uh, that is the case of a closed system where the fluid is not flowing and stationary. You have three components of energy that contributes towards the total energy of the system. And if the fluid is flowing, as in the case of an open system or control volume, there are basically four components or four parts of energy that are associated with the energy of the fluid that is being provided to the system or that is essentially leaving the system. So if we look at the non-flowing fluid, the energy of the fluid is represented by small letter e. Since essentially the fluid is not flowing, you attribute this energy to the system itself, such as in the closed system, the energy of the system is basically that of uh, internal energy represented by small u, the kinetic energy, and the potential energy, all of them expressed in per unit mass. So for a unit mass, there are these three components that contributes towards the total energy of a system as the fluid is not flowing. However, when we are talking about the flowing fluid, as in the open system, we represent the energy of the fluid that is associated with the system with theta, and it has four components. The additional component is PV, which is the necessary energy to to uh, to have a continuous motion of fluid throughout the system. So this is an additional energy other than this E energy, which is again the part of closed system also. Other than this energy, you have the energy requirement for the fluid to keep moving through the system. So there are four components: the flow energy, the internal energy, the kinetic energy, and the potential energy. These four components are basically contributing towards the energy which is being provided to an open system per unit mass. So again, this whole energy equation is dependent upon per unit mass. It is now dependent upon the amount of mass that is entering to the system, which will determine the total energy being provided to the system as a result of mass coming into the system. Anyways, we are also familiar with the combination property enthalpy, which is essentially internal energy plus flow work. So this combination enthalpy, this can replace and modify the energy of the flowing fluid in terms of enthalpy plus kinetic energy plus potential energy, obviously per unit mass. And the flow energy, which is PV, it is automatically taken care of by enthalpy, as enthalpy incorporates both internal energy and PV. And this is one of the reasons why we use this combination property enthalpy. It it helps us simplifying the equation. All right. Is it clear so far?
Yes, sir.
All right. Now, again, the summary: non-flowing fluid, you have internal energy, kinetic energy, and potential energy as a through three components for non-flowing fluid. Non-flowing fluid, you are basically referring to closed system, where the fluid is essentially stationary. Flowing fluid, you have four components. The additional component is the flow energy, and the three components, internal, kinetic, and potential energy, are the same as you have that in closed system. So this part basically refers to the energy which is being coming into the system as a part of open system. Now, both these energies are associated with mass as they are expressed per unit mass. So the total energy that would contribute, or the energy, the total energy that would contribute towards the energy of the system in terms of mass would be the E mass. This is nothing but mass multiplied by the energy per unit mass of the flowing fluid. So theta represents the energy of a unit mass that is becoming the part of your system, and if you multiply it by the mass which is coming into the system, it would contribute the total amount of energy that is becoming the part of system as mass is entering the system, or it is the energy which is leaving the system as the amount m amount of fluid leaves the system. Similarly, if we talk about the rate at which the energy is entering into the system, uh, or the rate at which energy is being transported into the system, we'll represent by E dot mass, because this energy is associated with mass essentially. So the mass flow rate, the rate at which mass is entering into the system, multiplied by the energy per unit mass that is being carried by that amount of mass, is basically the rate at which energy is being becoming part of the system or is interacting with the system. I hope this equation is clear to you. Is it?
Yes, sir.
All right.
Yes, sir.
All right. For a specific case where your kinetic and potential energies are zero or negligible, in such a case where your kinetic and potential energies are negligible, you have a very simplified equation for the energy in terms of mass. So the energy associated with mass is simply mass multiplied by the enthalpy, and the rate of energy associated with the open system in terms of mass is mass flow rate multiplied by the enthalpy of the system, or it is basically enthalpy per unit mass. Having this in mind, we come to the point where it says that most of the engineering systems, power plants, the components associated with power plants, they operate essentially operate under steady state conditions. That means a process through which fluid flows through a control volume, although it's an open system, but the flow rate and the properties of the control volume, they remain constant with regards to time. So, if we talk about the control volume where mass is flowing in and mass is flowing out in real time, or in real applications, you have the mass of the control volume and the energy of the control volume. It essentially remains constant under steady state conditions. And this is the condition under which this power plant essentially operates. Number two, the properties at the inlets and the exits. If you're talking about control volume being uh, under steady state condition, you are essentially saying that the properties at the inlet and the outlet, they are essentially not changing with time. So with this in mind, we move on towards the mass and energy balance equation for steady flow processes. Now we were moving towards how to apply the mass and energy balance equation for open systems we are which we are assuming, or which basically are very much close to the real time processes where systems are operating under steady state conditions. Uh, as we had looked into the energy balance equation for closed systems, I had mentioned this in the introduction of this chapter, that we'll have two balances in this control volume for open systems. One is the mass balance, and the mass balance for open systems. Can you give me an idea what should be the mass balance for an open system which is operating in a steady state condition?
So mass
Mass
flow rate
flow
at
rate will
both
be
points
constant.
constant or
Sorry, one by one, one by one.
so mass flow rate at both
The mass
inlet and the outlet will be equal.
All right. Yes, Izhar.
Yes, sir, so same. Mass flow rate will be constant. Mass entering and mass outlet at the same time will be constant.
Uh, this is when you have one inlet and one outlet. In a more generic way, you say the summation of the mass flow rate, the rate at which mass is entering into the system, sum of all the rates at which the mass is entering into the system through various inlets is or should be equal to sum of all the mass flow rates, the rate at which the mass is leaving the system from all the exits. Yes, in a simplified form, when you have a single inlet and a single outlet, you would say the mass flow rate 1, which is at the inlet, is essentially equal to the mass flow rate at the exit, which is m dot 2. Or if you have to express this in terms of rho AV, you would say that the product of density, average velocity, and cross-sectional area at the inlet should essentially be equal to the product of density, average velocity, and cross-sectional area at the exit. Now, this equation could further be simplified if you have an incompressible substance. In an incompressible substance, the density rho 1 is equal to rho 2 equals to rho. So that means you would essentially have this to cancel out again for an incompressible substance. This means that the volume flow rate at the inlet should essentially be equal to the volume flow rate at the exit. But this is for incompressible fluids. All right. Moving on towards the second part, which is energy balance equation. You have energy balance equation which says that E dot in minus E dot out is equal to change in energy of the system per unit time. Since you are referring to the system as a steady state system, that means the change in energy of the system with regards to time, change in time, would essentially be zero since you're talking it to be a steady state system. This means that E dot in is essentially equal to E dot out, that whatever the rate at which energy is coming into the system by heat, work, and mass, summation of all the three mechanisms, is essentially equal to the rate at which energy is leaving the system again by the three mechanisms: heat, work, and mass. Now, the mechanisms may, in the sense, there is a case where the energy coming into the system is more in terms of heat and less in terms of mass, and there is no work, but it is leaving in the form of mass more, and lesser amount is being uh, released in the form of heat, and there is essentially no work. So there could be interconversions between the mechanism, but essentially the overall rate at which energy is coming into the system should be equal to the overall rate at which energy is leaving the system for a steady state open system. And once you look or you split these three mechanisms into individual forms, you would come to know that uh, Q dot in, the rate at which heat is coming into the system, plus W dot in, the rate at which work is being done by the system or on the system, uh, plus M dot theta. This in summation in represents all the inlets. M dot theta represents the rate at which energy is coming into the system in terms of mass. This should be equal to the rate at which heat is leaving the system, work is done by the system, and again, the out summation refers to the outlets. M dot theta refers to the energy leaving the system uh, in terms of mass. Uh, as I have mentioned, theta could be further modified into three categories: enthalpy, kinetic energy, potential energy. Enthalpy, kinetic energy, and potential energy of the fluid. Enthalpy already incorporates the internal energy plus flow work. It already incorporates that. So it's a uh, combination property. Now, there's one more thing which we had already mentioned also in closed system also. At times you will find that if I want to modify this equation, I could bring Q out onto this side with a negative sign. That means I could say that Q dot in minus Q dot out, this would be the left hand side in terms of heat, the rate of heat being supplied to the system. If I bring Q out onto this side, this can be expressed as Q net in or it could also be expressed as simply Q dot. So this expression could also be represented by this, or this could also be represented by Q dot. Similarly, I can bring W out onto this side with a negative sign. That means it could be W out minus W in. This could also be represented by W dot net out of the system or simply W dot. When I bring W out onto this side, I can express W out minus W in with this expression or simply W. All right, is this clear?
Yes, sir.
All right,
Yes, sir.
all right, great. So when you look at the equation over here, you have simply simplified it. You have taken the mass, energy associated mass flow rate onto the right hand side, which means the energy flowing out of the system in terms of mass minus the energy flowing into the system in terms of mass flow rate. This is essentially equal to Q dot minus W. Q dot is essentially Q in minus Q out, and W dot is essentially, since you have a negative sign, you have minus W out minus W in. This would essentially become, if you open up this equation, it would become the equation that we have seen on the previous slide. So you could represent W with W out minus W in and Q with Q in minus Q out. That means heat input and work output both are considered as positive. This is all positive. This is all positive. Anyway, so this is the expression in which you could modify your equation. Now, if you have a single inlet and outlet, you can bring the mass flow rate. If you have single inlet and outlet, you essentially have mass flow rate 1 equals to mass flow rate 2. That means the inlet and outlet is one inlet and one outlet. In such a case, this mass flow rate would be represented by M, and you would essentially have H2 minus H1, V2 square minus V1 square, and Z2 minus Z1 as your expression. If you want to get rid of mass flow rate, you can divide Q dot by mass flow rate, and Q dot divided by mass flow rate or W dot divided by mass flow rate would essentially cancel out the time constraint, and you will essentially have Q and small w, that means energy per unit mass. So if you divide it by the mass flow rate, you'll have heat per unit mass, work per unit mass, and these quantities are already per unit mass. So this would be your per unit mass equation. Again, if you have a simplified form where the kinetic and potential energies are negligible, you can express the equation by neglecting these two. These two approximately equal to zero would lead to Q minus W is essentially equal to change in enthalpy. And this I've already expressed that Q is essentially Q dot divided by M dot and W is W dot divided by M dot. Uh, One thing you should be careful of that in a control volume, the only kind of work interaction that you could have is essentially the electrical work or the work associated with the movement of shaft. So in an open system under steady state operations, shaft work and the electrical work, they are the only forms of work that a simple compressible system may involve in. Uh, this is the energy balance equation and the mass balance equation for an open system and operating under steady state conditions. Now, we'll move on towards the important part of the fifth chapter, where you will consider many engineering devices. They operate under steady state conditions for long periods. That means the components of steam power plants such as turbines, compressors, heat exchangers, pumps, they operate non-stop for months, and it is only for a certain period of the year where the plant is being shut down for maintenance and the equipment they are not working. Otherwise, they are working continuously day in and day out under steady state conditions. So these devices, they can be very conveniently and very accurately assumed to be working under steady state conditions. And these devices are essentially known as steady flow devices. So the steady state equation that we have developed in the last slide, we'll try to apply this equation on different components of power plants or different components that are involved in engineering applications. So the first set of components on which we'll apply this equation is essentially the nozzles and diffusers. Nozzles and diffusers, we'll try to understand what their functions are, and then we'll try the energy balance, apply the energy balance equation on nozzles and diffusers. These devices, nozzles and diffusers, they're commonly encountered in jet engines, rockets, and spacecrafts, complicated applications, complex engineering applications, and they could be applied on as simple as application as that of garden hoses. Now, the function of nozzle is essentially to increase the velocity of a fluid. The primary function of nozzle is to increase the velocity of the fluid, and this is done at the expense of pressure. So by reducing the pressure of the fluid, uh, or by decreasing the pressure of the fluid, essentially the velocity of the fluid is being increased in a nozzle. Diffuser works in an exact opposite manner. The function of the diffuser is that it basically increases the pressure of the fluid by slowing it down or by decreasing its velocity. So uh, here is the geometric representation of nozzle and diffuser. The prime reason for which a nozzle is called a nozzle is that the velocity at the exit, velocity of the fluid leaving the nozzle is much higher as compared to the inlet velocity. Similarly, the velocity of the diffuser in diffuser, the primary function is the velocity at the exit is much smaller than that at the exit. Now, the geometric representation, if we think of nozzle, the obvious picture that we have in our mind is that the cross-sectional area in a nozzle reduces in the direction of the fluid motion. Fluid is moving in this direction, so the cross-sectional area would reduce in this direction. This is the geometric picture of nozzle that we normally have in our mind. And the diffuser, the picture of diffuser is exactly the opposite, that the cross-sectional area is increasing in the direction of fluid motion. This is true, but this is conditional. This geometric representation is correct for the flows where we have subsonic flows. Subsonic flows, that means the flows in which the exit velocity, the velocity at the exit V2 is less than the velocity of sound. In such a case where you have subsonic flows, that means the velocity at the exit remains less than the velocity of sound. This is correct. That you have reducing cross-sectional area for the new nozzle and increasing cross-sectional area for the diffuser. But where you have supersonic flows, in supersonic flows, you have the velocities greater than the velocity of sound. In such a case, nozzle would have an increasing cross-sectional area in the direction of fluid, and the diffuser would have reducing cross-sectional area in the direction of fluid. It would be the exact opposite for supersonic flows, the geometric representation. The function remains the same. So the cross-sectional area of a nozzle reduces in the direction of flow for subsonic flows and increases for supersonic flows. And the reverse is true for the diffuser. That means the cross-sectional area increases for subsonic flows and decreases for the supersonic flows in the direction of flow. Now, coming towards the energy balance equation for the nozzle, the generic energy balance equation is that you have heat, the heat transfer between the nozzle and the surrounding. If nozzle is your system, the heat transfer rate is essentially zero. Since the fluid is moving at a very high velocity, essentially, I mean, it's not necessary, the heat transfer rate is very much negligible. So you normally assume it to be zero unless and otherwise specified. Similarly, the work done associated with nozzle, there is no electrical work, no shaft work associated with nozzle. So the work done or the rate of work done by the system or on the system is essentially zero for nozzles. And the change in elevation of the fluid or change in potential energy of the fluid is essentially negligible. So if you have these three terms discarded, the energy balance equation would essentially be dependent upon the enthalpy and the velocity of the fluid at the inlet and at the exit. Since you have steady state system, mass flow rate is the same if you have one inlet and one outlet. So you will have essentially the summation of enthalpy plus kinetic energy per unit mass at the inlet should be equal to the summation of enthalpy plus kinetic energy per unit mass at the exit. So this is the conversion that is taking place. Velocity reducing or increasing would have an effect on the enthalpies, corresponding enthalpies. This is the equation for nozzles and diffusers. I hope it is clear so far. Is it clear so far?
Yes, sir.
सर क्वेश्चन है सर
Yes.
जी जी जी
सर आपने सर एक वो सुपरसोनिक के लिए सर जो कंडीशन बताई सर इन दैट केस हमारी वेलोसिटी इंक्रीज कैसे होगी फॉर नोजल्स एट द एग्जिट
तो नोजल्स का फंक्शन क्या है?
सर वो तो सर जब हमारी ज्योमेट्री सर वो हो रही है डिक्रीज हो रही है सबसोनिक के लिए तब तो सर
जी
समझ आ रहा है कि सेकंड क्रॉस सेक्शनल एरिया इज लेसर देन द फर्स्ट क्रॉस सेक्शनल एरिया सो द सेकंड वेलोसिटी विल बी ग्रेटर लेकिन सर अगर सेकंड क्रॉस सेक्शनल एरिया इंक्रीज हो रहा होगा तो फिर वेलोसिटी कैसे डिक्रीज होगी सॉरी इंक्रीज होगी
because you're talking about subsonic flows वहां पे ये equation valid नहीं होगी. I mean I'll not go into detail कि density कैसे change होगी क्योंकि this is all related to how the density is changing when you're talking about fluids or air because you have rho AV uh, uh, as the mass flow rate. So since you're talking about mass flow rate because you have multiple factors if you look at this equation mass flow rate is equals to rho AV. Now you are attributing everything to this cross sectional area. आप ये कह रहे हैं mass flow rate constant है और जैसे जैसे डेंसिटी भी कांस्टेंट है और जैसे एरिया रिड्यूस हो रहा है वेलोसिटी जो है उसके ऊपर इफेक्ट आ रहा है वेलोसिटी इंक्रीज हो रही है दिस इज व्हाट यू हैव इन योर माइंड इज दिस और इज इट नॉट सो
सो सर एक्चुअली व्हाट आई हैड इन माइंड वाज सर मास फ्लो रेट में हमने सर अगर हम दो उस पे हैं सर V1 और V2 के लिए अगर हमने तो हम इनकम्प्रेसिबल फ्लूइड के लिए बेसिकली डेंसिटी को कैंसिल आउट कर देते हैं इक्वल होती है सर आप कहना चाह रहे हैं कि फिर ये इनकम्प्रेसिबल नहीं रहेगा
जी एग्जैक्टली यू
ओके सर
वोंट हैव दिस इक्वेशन ए वी ये वैलिड नहीं होगी कि क्रॉस सेक्शनल एरिया रिड्यूस हो रहा है तो वेलोसिटी इंक्रीज हो रही है दिस वोंट बी वैलिड इन सच अ केस जब आप इतनी हाई स्पीड पे चले जाते हैं तो डेंसिटी वुड आल्सो बी अ an important factor clear
ओके
change density पे भी आना शुरू हो जाएगा is this clear
ओके सर यस सर
will not go more into details because you have a complete chapter on these nozzles in Thermo 2. So I'll not go into subsonic and supersonic flows at the moment, but just to give you an answer, uh, the density would also be a factor then. All right,
यस सर
great. Now, we have looked into the example associated with nozzles and diffusers. Now, we'll be looking into an example associated with diffusers, which says that air. Now I have highlighted air. Why? Any idea? I have highlighted it for the fact that now if I can assume air as ideal gas and I can use the tables associated with ideal gas for air when I have air as a fluid. Air at 10 degrees centigrade and 80 kilopascal, it enters into the diffuser of a jet engine steadily. That means you have steady state condition with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 meters square. The air leaves the diffuser with a velocity that is very small compared with the inlet velocity. That means you can assume V2 to be almost equal to zero. The change in velocity is essentially zero. So it means that the mass flow, you have to determine the mass flow rate of the air and the temperature of the air leaving the diffuser. These are the conditions. These are the conditions given to you in terms of pressure and temperature. This is velocity and cross-sectional area given to you. You have to determine the mass flow rate of the air and the temperature at the exit. So, any idea how I can find out the mass flow rate of the air?
So rho A V.
Density find करेंगे और that's your area given.
All right. So the first step is to write down the formula for mass flow rate, which is rho A V, rho 1, A1 and V1. V1 and A1 are given to you. I have to find the density. कैसे find out करूँगा density?
सर रो इज इक्वल टू पी ओवर आर टी से हम कर सकते हैं सर आर एयर के लिए हम निकालेंगे
सर आइडियल गैस इक्वेशन यूज करेंगे
Yes,
assumption
that
वाला.
is very good. So that is the reason I highlighted air as an ideal gas. When you have the ideal gas, you can apply the ideal gas relation where rho V equals to RT, and you can say that V is equals to RT over P. Temperature is given to you, pressure is given to you. R for air is an ideal gas. You can find it from the table. If you have specific volume is essentially 1 over density. All right. So essentially you have R value from the tables for air. Temperature again in absolute scale, Kelvin. Pressure is given to you. You have all these three values. You can find out the specific volume. Once you know the specific volume of the fluid, the mass flow rate is the volume flow rate, V dot, divided by specific volume, or density multiplied by velocity multiplied by area. Density is essentially 1 over specific volume. This would give you the volume, the mass flow rate. Now, if I know the mass flow rate, how can I find out the temperature of the air leaving the diffuser? I'll simply write the equation for you in terms of energy balance. If you look at the energy balance equation, it is m dot h1 plus v1 square over 2 equals to m dot
Enthalpy से find
into H2 plus V2 square over 2. Now, all right, I'll write it over here a little more clearer. M dot 1 into H1 plus V1 square over 2 is equal to M dot 2 into H2 plus V2 square over 2. M dot 1 and M dot 2 are they same?
यस सर
So they would essentially cancel out. You will have H1 plus V1 square over 2 equals to H2 plus V2 square over 2. Now V1 is given to you. What is V2?
जीरो सर
Almost zero. Now H1, can you find out H1 enthalpy at this condition?
यस सर
The enthalpy of an
टेबल यूज
ideal
करेंगे.
gas. एक minute. Enthalpy, thank you. Enthalpy of an ideal gas is dependent upon what?
CP
And CP is dependent upon what?
temperature.
Yes. So essentially, you know that enthalpy of an ideal gas is more of dependent upon the temperature only. So if you remember, we had three ways how we can find out the CP of or enthalpy uh, of an ideal gas. If you go back and recall, table A17 is one of the mechanisms in which is the ideal gas table for air, where you can find out the enthalpy corresponding to the given temperature. So if you go to table A17, you can find out the enthalpy for the temperature given. You can find out temperature is 10 degrees centigrade, which is 283 Kelvin. For this temperature, you can find out the enthalpy, which is your H1. So can you find out H1?
यस सर
Yes or no?
Yes, sir,
यस सर
temperature given है.
All right.
यस
So you can find out H1, you know V1 square or V1, you know V2 is 0. Can you find out H2 then from the equation?
यस सर
If you know H2, can you find out the temperature?
Yes, sir. Change in enthalpy will be equal to CP into change in
No, please no. The way you have found out H1 is the same way you'll find out temperature. Right now, what you did was you had a temperature and enthalpy table. You went to 283 Kelvin and you read out the value, that is the value of H1. Now you have found out the value of H2. So you'll go to the enthalpy and read the corresponding temperature in terms of enthalpy. That's the simple way. Clear enough? Don't
Yes,
know
sir.
Yes, sir.
CP and DT in this. So heat transfer, as I mentioned, it is negligible or have not been mentioned, so it is negligible, zero, no work associated, no change in potential energy. You have a simple equation where m dot h1 v1 plus v1 square over 2 is equals to m dot h2 plus v2 square over 2. Mass flow rate would cancel out. You would have h2 as the subject of the formula. H1, you will find out again h at 283 Kelvin. H at 283 Kelvin again from the table is 17. Plug in the values 283. This is H1 known to you, velocity known to you. You will divide it by 1000, the velocity, the energy associated with velocity. Why? Because enthalpy is in kilojoules. Once you have that, you'll have the value of H2. Once you have the value of H2, you'll go again to table A17. You'll go to table A17 and read the corresponding temperature, which comes out to be 303 Kelvin. Clear enough?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right. So I'll stop over here